In the chapter 6, I will talk about the inverse kinematics of the robot system. Okay, let me read the first sentence. For general n degree of freedom open chain, not closed chain, with pod kinematics, T theta belonging to SE3. The inverse kinematic problem can be stated like this. Okay, for a given homogeneous transform, maybe this X is represents the desired posture of the robot and effector frame. At the time, we'd like to find solution theta satisfying this constraint. Okay, from here, we should find out the theta sequence. Okay, let's take an example, simple example. The number of the inverse kinetic solutions will be, in this case, if you specified the target here, maybe it cannot be described using the disorder system. At that time, there is no IK solution. On the other hand, the target is specified like this. Maybe at this boundary, we will have only straight solution. So we have one. Inside the workspace from here, inside the workspace, any point is specified. At that time, we have two IK solution, as you can see in this equation, in this figure. So we have two. Like this, there are many IK solution according to the robot configuration. Especially in the case of the twinkle planar robot system, we have two. Okay, when there are two solutions, they are called, this posture is called as left solution. On the other hand, I'm sorry, this is the righty solution. This is the lefty solution. So it is the left and right. Sometimes elbow up and elbow down. Maybe you can imagine the elbow up posture or elbow down posture. So in the case of the Puma robot system, Puma 560, there are four kinds of IK solution for the constant for specified desired posture. One posture, four IK solution. That is called as lefty, right, elbow up, and elbow down. Okay. In this Turing planar manipulator, left and right solutions exist. Okay, one more. I'm sorry. Okay, let's calculate the end effector position using the theta 1 and theta 2. It's very easy. So Aaron cosine theta will be this one, and we can make another triangle. Okay, this is the theta 1. So L2 cosine theta 1 plus theta 2, L2 cosine 1, 2. By adding Aaron cosine 1 plus L2 cosine 1, 2 will represent the x coordinate of the end effector of the resistor system. Maybe using the sign, we can represent the y coordinate of the end effector. Okay. Using the cosine law, using the law of cosine, okay, we know that this is the beta can be represented using the cosine law. It's very easy. L1 square plus L2 square minus 2 times L1 L2 cosine beta will be equal to this one. This can be represented by the square root x square plus y square, right? So we can get this equation. Okay, here we know that every element without beta, so it can be represented by using the arc cosine to obtain the beta, like this. After obtaining beta, then the theta 2 can be represented very easy way. Anyway, the beta can be obtained like this, and alpha can be obtained using the similar way. So L1 square and x1 L1 square plus x1 plus y square minus 2 times this one and this one, and the cosine alpha will be equal to L2 square, like this. So we can calculate alpha angle. So by using the beta and alpha, okay, we can okay, in this case we can obtain the theta 1 and the theta 2. Okay, maybe the theta 1 will be gamma. Gamma can be obtained arc tangent y over x from the end effector. The minus alpha will be equal to theta. So we have this equation. On the other hand, okay, from the pi minus beta will be equal to theta 2. So we have this one. Okay, this is called as light solution. On the other hand, left solution will exist like this. Okay, and then gamma plus alpha will be the theta 1, and the minus pi plus beta will be equal to theta 2. So we have this one. Okay, because the theta 2, every joint angle will be represented positive in the case of counterclockwise. Okay, counterclockwise will be positive, but the theta 2 is counted as a clockwise. In the case, negative value will be obtained. Okay. On the other hand, the end point lies outside the range of the workspace. Then there is no solution. That is called as singularity. Okay, section 6.1, Analytic inverse kinematics. In this section, we will deal with the two kinds of traditional conventional robot system, such as the Puma 560 and the Stanford arm. Actually, the Stanford arm is very similar with the Puma 560, except the third joint, elbow joint, is replaced with the prismatic joint. Other one is the same with the Puma 560. A long time ago, the Puma was very famous. When I was PhD student, our lab has the Puma 560. At that time, we drive the dynamic equation, dynamic parameters, inertial matrix, and Coriolis centrifugal matrix from the experimental data. Okay. Anyway, the Puma 560 was traditional model to study the robot system, especially kinematics and dynamics. Anyway, if you understand how to solve the kinematics and inverse kinematics of Puma 560, maybe you can extend your knowledge to the other types or new type of robot system. So I'd like to recommend you to memorize or learn how to solve the kinematics and dynamics and control. Okay. Okay. First issue is the analytic inverse kinematics. Analytic inverse kinematics is very intuitive to solve the angular value from the end effector Cartesian position. In many cases, we are using the Jacobian in the level of the velocity, in the level of velocity. In that case, the mapping joint space and task space will be the linear, but analytic in the position or configuration case, the mapping is non-linear. As you know, the homogeneous transform has many sine and cosine, so the 4x4 homogeneous matrix is embedded at the 16-dimensional homogeneous transform is embedded to the 6-dimensional space. So 10 constraints exist in the homogeneous transform. Like this, the linear mapping using the Jacobian will be better. Nowadays, the Jacobian is used to solve the inverse kinematics, not the computation level. Okay. Anyway, we will study first the analytic inverse kinematics, and then the next lecture I will talk about the velocity level IK solution. I'd like to recommend you to use the velocity level IK. Okay, maybe we will use the POE space form. Okay, so after assigning the square axis S1 and S2, S3 and S4, S5, S6, and then the 0 position will be assigned as M. So we can write down the pole kinematics using the POE. Okay, the IK position level IK will be reformulated like this for given X belonging to SE3 homogeneous transform, and IK problem is to find solution theta belonging to R6 because we have the 6-dimensional theta satisfying this nonlinear equation. Okay, as a typical example, we derive analytic inverse kinematic solution for Puma and the Stanford arm. Okay, Puma 6R. Puma is composed of the 6R. Okay, the Puma arm is placed in each 0 position. Actually, there is 0 positions like this. This is the X, this is the Y, this is the Z. 0 position, this is the electric motor, and this is another electric motor, and the y-axis maybe. Okay, and the third joint angle is here. Okay, so this is the x0, y0, and z0. Okay, like this is the list center. List center has the 3 orthogonal joint axis. Okay. So okay, the 2 shoulder joint axes intersect orthogonally at the common point. With the joint angle or joint axis 1 is aligned G. Is it right? It's aligned G, and joint axis 2 is aligned Y. Okay, the Y. This is theta 2, and this is the theta 3. So joint axis 3 lies in the xy plane, and it is aligned with the parallel with the joint axis 2. So this is theta 1. Okay. Joint axis 4, 5, 6, the list center intersect orthogonally at a common point. It is called as the list center to form the orthogonal list. For the purpose of this example, we will assume that these joint axes are aligned in an order of G, Y, X. So we will utilize the GYX Euler angle to extract the angles from the rotation matrix later. Okay, and the length of the link 2 and 3 will be denoted by the A2 and A3, and the first joint angle is denoted by the theta 1 and the theta 2 and the theta 3. Okay, this point is the least center. Okay, the x-axis px, y-axis py, the z-axis pz. So in order to solve the problem easily, we will make the plane. This plane is aligned with R and Z. Okay, to solve the theta 2 and the theta 3 in the by assuming this robot system as a planar case. Okay, this arm may also have an offset and may have offset at the shoulder. Actually, the Puma has the offset. Okay, like this. Actually, as mentioned before, this is aligned with the y-axis. Okay, y-axis. Okay, we have this kind of offset. Okay, so by rotating the theta 1 as a 190 pi, maybe we have this posture. Okay, you're right. So this kind of concept will be utilized to solve IK. The IK problem for the Puma type arms can be decoupled or divided into inverse position and inverse orientation. We will separate one problem into two. So first one is called as inverse position problem and inverse orientation problems. We will decouple each other. Okay, we will consider two cases, zero offset first, and then deal with the non-zero offset later, next page. Okay, D1 S0 in that case, consider a simple case for of a zero offset Puma type. Okay, express all vectors in terms of the fixed frame coordinate and denote the component of the least center. Okay, least center will be denoted by the px, py, pz. Okay, this least center will be projected into the x and y plane. So this point will be px and py. Okay, so it's very easy to obtain the theta 1 by using the arctangent 2. So arctan 2 is used to express the theta 1. Okay. In addition, we can get both theta 2 and theta 3 from RPZ. Actually, after obtaining theta 1, theta 2 and theta 3 will be calculated by making a planar plane, this plane. How about that? This plane is RZ plane, okay? After making an RZ plane, and then we will apply the Turing manipulator kinematics. It's very easy. So in the previous problems, we have talked about how to solve the theta 2 and the theta 3 in the planar case. From this point, by making a triangle, this angle will be determined using the law of cosine, and then we will obtain the theta 3, and then by calculating this angle, theta 2 will be determined by subtracting from here and here, so we can determine the theta 2. Okay, maybe if you are good at solving the Turing planar manipulator case, it's not difficult. So theta 2 and theta 3 can be calculated using the 2 or just the cosine. Okay, second solution. Okay, let's consider the second solution of this Puma type. Okay, after setting set at 0 theta 2 and 0 theta 3, maybe the theta 2 angle of the end effector will be denoted, will be located here. Okay, by assuming the theta 0 theta 2 and 0 theta 3, maybe we have this kind of manipulator. Okay, let's rotating pi 118. Then we have this manipulator from here to here. Okay, maybe the theta 1 plus pi will be this kind of a manipulator. And then by applying the theta 2, okay, this manipulator, let's apply the theta 2 to the pi. How about that? To the pi. Maybe to the pi. Then we will get the same one. Is it right? So, okay, here's theta 2 is applied to like this. Then maybe the pi minus theta 2 will be this one. Okay? And then applying the theta 3, we will get the same manipulators. Okay, let's explain it again. Okay. From this configuration, by adding a pi, we have this kind of manipulators. Okay, and then this angle is the theta 2. So by adding the pi again, maybe if you apply the pi angle to here, then we have this kind of manipulator. Okay, then this angle should be reflected to here. So minus theta is applied. So we have this one. Maybe you can imagine how to obtain the same posture from different way. So theta 1 will be the tan 2 px and py plus pi. And then if you apply the theta 2 as a pi minus theta 2, then we have the same computation. Okay? As long as the non-zero px, non-zero py, these two solutions will be very valid. Okay. On the other hand, if you have the 0 px and 0 py, in that case, there are many theta 1. Maybe you can assign the theta 1 as a 90. It's okay. We have the same posture in viewpoint of the endpoint. Okay, so theta 1 can be determined anyone. This kind of computation is called as singular. Okay, there are many, infinitely many possible solutions for the theta 1. Okay. Okay. For the practical issue, the Puma 560 has the offset. Okay. Puma 560 in the okay, as you know, this axis is aligned with the okay, this axis aligned with the y. Okay, and 0. In this case, D1 is non-zero. Okay. In here, there will be the two solutions for theta 1. One is left the other one is the light. Okay, let me explain in detail. Okay, this posture is called as righty. This is lefty. Okay. So the lefty case is easy to obtain. Okay, this point is determined from the Cartesian coordinate px and py. So it will be denoted by the pi, and the minus alpha will be equal to theta 1. So the pi will be denoted by the arctangent py over px. And the alpha is the constant value. Arctangent, this one is will be calculate d1 over arctangent r square minus d1 square. Okay, r is determined from px square py square. Okay, so theta 1 is obtained very easy way, pi minus alpha. Okay, from here and here. It's not difficult. Okay, but in the case of the light solution, we should consider more detail. Okay, from the zero left solutions, as you know, theta 1 is 0. At that time, we have this kind of manipulator system, x0 axis, y0 axis. Is it right? Okay, this manipulator will be assigned like this. So we have this kind of configuration. Okay. Here, let's apply the pi. Let's apply the theta 2 as a pi. Okay. Maybe the configuration will be moved to here, like this. Okay. Okay, the theta 1 is 0, but by applying the theta 2 as a pi, the end effector coordinate is greatly varied into here. Okay. And then let's apply the 90 degree to the theta 1. Okay, this will be this one. So D1. Okay, you right? One more. If you consider theta 1 as 190, maybe we have this one. Is right? Here, if you assign the px and the py as a target, okay, this value is equal to pi from the definition of from this definition. Okay, here this is the d1. This is the r. So if you are applying this pi angle, then this will move to here. Is right? And then by adding a pi, this point will be approached to here. So theta 1 will be pi plus alpha, because this is denoted by the alpha, plus pi. So that's my assertion. Okay, the textbook shows another representation of this equation, but I don't agree with this equation. I think it is right, but if you don't think my opinion, let me know the reason why, you think so. Okay. I think the theta 1 should be obtained pi plus another pi and plus alpha. Okay. Okay, determining the angle of theta 2 and theta 3 for the Puma type arms now reduced to IK to the Planetary manipulator training. It's very easy. So let's make the R, in this case, R minus R square minus D1 square axis and PZ axis. Okay? Maybe the theta 1, the theta 2. I'm sorry, the theta 2 and the theta 3. Okay? Let me draw it again as a big picture. Okay, draw it again. This axis squared R square minus D1 square. This axis, the PZ. The theta 1, this is the A2 and the A3. Okay, A2, A3. Theta 2, theta 3. Okay, this is the least center. And this point will be denoted by the PZ square and this term square. So, as explained in the previous slide, the beta angle can be calculated very easy way. Okay, A2 square, A2 square and A3 square minus 2 times A2 A3 cosine beta will be equal to PZ square R square D1 square. R square implies the PX square PY square. So the cosine beta will be equal to cosine pi minus theta 3. In this case, it should be equal to cosine theta 3. So the cosine theta 3 can be calculated like this. It's not difficult. So you can write down. I can write down this equation very easily. Okay. And then if you know the cosine theta 3, and then let's make another rectangle. This is the theta 3. The cosine theta 3, if you denote the cosine theta 3 as a dt, at that time, this will be this is the 1 and the d. I'm sorry, this is the d. 1d, and this will be the 1 minus d square. So the theta 3 can be obtained using the arctangent 2 from this relation. So we have this one. Okay. Anyway, you can apply the arc cosine. On the other hand, you can apply the arctangent 2. I think the arctangent 2 has the wider range to represent the angle. So I'd like to recommend you to use the arctangent 2. Okay, two solutions for theta 3 correspond to elbow up and elbow down. So if we choose the plus or minus, it will depends on the computation. They are called as elbow up and elbow down. Okay. On the other hand, theta 2 can be obtained. In the previous slide, after obtaining this angle, theta 2 is determined using this relationship. But on the other hand, by making another rectangle, okay, maybe this total angle will be the pz and r square minus d1 square. By applying the atan 2, this value will be equal to this angle. And then the second link is still projected to the this direction. So A3 cosine 3, C3 will be the this distance. This will be the A3 cosine sine 3. So by adding A2 plus A3 cosine 3, and then as a height A3 cosine 3, this angle can be obtained. So we can use this relation. Okay. Okay. So this is more general compared to by subtracting from here to here. This atan tool will show the more general case because it has a wide range to represent the angles. Okay. As mentioned before, the upper figure shows lefty solution, elbow up and elbow down. The bottom figure shows the righty computation one solution, elbow up and elbow down. So Puma type has 4 solutions. In the case that the offset exists. The posture in the upper panel or lefty, I have explained it already. Okay. Let's solve the IK orientation problem to find out the theta 4 through theta 6 given and beta orientation. Okay, from the POE, let's divide the POE equation into the known term and the unknown term. Maybe the theta 4 through theta 6 terms will be unknown. After obtaining the theta 1 and the theta 2 and the theta 3 using the kinematics, we can know that the right term. Okay, this is known, so we can make the numerical value from the known variable. Okay, maybe the S4 square axis, post joint square axis will be the g-axis, and y and z. Maybe we will have zero linear velocity because the list center we have the common list center. Okay, orthogonally aligned. Okay, list joint angle theta 4 through theta 6 can be determined from this equation. Maybe we can write down, we can extract rotation matrix from here. From this homogeneous term, we can extract the rotation matrix as a numerical value. And then, as you know, the first term is g-axis rotation, y-axis rotation, and x-axis rotation. So we can extract GYX Euler angle from rotation matrix R. This procedure is suggested in the appendix B in your textbook. Okay, it's not difficult. If you read the appendix B, maybe you can understand how to extract the GYX Euler angle. In there, there are many materials to extract the angles. Maybe I remember that the square axis rotation and I'm not sure the Lorentz angle extraction method exists in there. Okay, last page is about the Stanford arm. Stanford arm is very similar with the Puma 5660. Okay, the third joint, elbow joint, is just replaced with the prismatic joint. So the kinematics is much easier than the Puma 560. But the first joint is the same. Second joint is the same with the Puma, but third joint, D3 or theta 3, is replaced with the prismatic joint. This is the least center, so it has the three orthogonal joint axes. Okay, so everything's the same. So theta 1 can be calculated from the projection point of the px and py using the r tan 2. So like this, we can get it. On the other hand, theta 2 can be obtained from the r z plane. R is determined square root px square py square, and s is determined pz minus d1. It has to offset in the g direction. Okay, so using these two data, we can determine the theta 2. Okay, let's consider the second solution. If we apply the pi, if you add the pi value to the theta 1, maybe it is located like this. Is it right? So by adding a pi to the theta 1 angle, we have the opposite configuration. Then let's apply the theta 2. Let's add the theta 2 to the pi. Then we have this one. So pi minus r tan 2 as r will show the same configuration by rotating theta 1 and rotating theta 2 will show the same. And theta 3 is very easy. Using this using the triangle, this is the orthogonal to each other. So a2 plus theta 3 squares will be equal to r square and s square. So we can determine the theta